Uh, Hello there. My name is Johnson Makmot, software engineering student and taking us through the large vision models for multi-disease retinal screening in Uganda healthcare, representing group 52. Moving on, so the background and introduction about this platform is the Retina's role is whereby it's a non-invasive window into both systematic and healthcare. The problem in Uganda, high prevalence of diseases like diabetic retinopathy, glaucoma, and hypertensive retinopathy. We also have current gaps whereby we have limited access to ophthalmologists, specialized screening equipment, especially in rural areas. Moving on, when you look at the recent trends, early AI in ophthalmology was focusing on single disease detection like diabetic retinopathy and also using traditional machine learning and simpler CNN and also limited generalizability and multi-disease capabilities. But now the advances here we are using LVMs, large vision models, transformers to show state-of-art performance and also knowledge graphs and graph-based reasonings. So problem statement is whereby our domain application problem is well, back in the days there was only one ophthalmologist to attend to over 1 million people. So East and Net World Health Organization was recommending at least one per 250,000 people. So that makes it very intense and it causes like a lot of population for people not to be attended to quickly. So here is our major issue why we are resolving this is because we are introducing something that is going to allow us to reach out to rural areas and increase the speed of working with what with the retinal AI. So the clinical challenge is multi-level complexity average 2.3 diseases per positive case, and the diagnosis accuracy, which has manual screening only 7 to 80%, times constraints are 50 to 20 minutes by expert diagnosis. So the computational complexities are multi-label learning, where we have exponential label space, medical image processing, where I have a resolution images with fine diagnostic details, severe class imbalance, and major class bias affecting rare disease detection, explainability requirements, and mobile deployment. So, specific objectives we are to develop a multi-disease classification system. Then we also deploy an age-optimized clinical system and establish an AI for clinical trust. We also evaluate the system performance against clinic standards. Then we're addressing technical, clinical, and deployment and validation in a, whereby we shall look at the required accuracy, the AI optimization, appropriate evaluation metrics, and architecture combination for multi-level classification. So our specific contributions to retinal disease detection. So we developed this multi-architecture ensemble framework to combine the efficient net, vision transformers, convex models to robust retinal disease classifications. We deployed this novel mobile optimization techniques, especially tailored for medical imaging, achieving 80% and 7% model size reduction. So this is our methodology. Our methodology is just data input pipeline. Then we process the data pre-processing pipeline. Then we also do the model training architecture. Then we train and validate. Then we explainability analysis, chain doing clinic development, and mobile optimization layer. So system architecture is a large vision model for multi-disease retinal screening, whereby we have the data input, which allows input of retinal images, then we pre-process them, then we go into the model layer whereby we have the feature extraction, graph construction, graph message passing, classifier. Then we move the model layer to the API where or the inference layer where we have the inference server with Gradio, Web UI, we have inference spaces and extensions. Yeah, so the data set description is the attributes are the details, the images, total images are 3,200. We have a training set of 2,240 images, validation set of 640, and test set of 320 images. Image format is PNG and red, green, blue color space. The resolution is 2144 by 1424 to 4288 by 2848. So the file size is 899 kbs and the disease type are four distinct pathological conditions plus normal. So these are the different graphs that show up by variate analysis, and these are the box plots, the violin plots, and the stacked bar chart. We have also the cross tabulation chart. So here the graph clip architecture, it operates by the input image that we put goes to the vision encoder, and also the text prompts input goes to the text encoder. Then they're all sent to the cross model attention, which depicts the knowledge graph and also the multimodal fusion, then gives the output. Then the visual language model, we have different scales which go to the feature pyramid, language grounding, and graph construction. Then we give it the GNN reasoning and get output. The scene graph transformer has the input, object detection, which gives us the relationship extraction, the scene graph, and the graph transformer, which provides the global text context pool and gives us output. Then we have the fourth model, which is the vision transformer, which gives the input, it does patch embedding, it positions the encoding, then it also does the graph builder, give us the GNN layers to the global pooling, and gives us the classification, the 45 classes. So our output results and discussions, we used the five-fold cross validation format, of which we used 80% for training and 20% for validation. Moving on, these are our comprehensive performance comparison, whereby these are mobile optimized models, and we have the macro F1 score, we have the precision comparison, recall comparison, accuracy comparison, and the AUC ROC comparison. So these are expected results per region, where the precision, recall, F1 score, specificity, and AUC ROC. So these are also still the continuation of the previous slide. Expected results and discussions, we have model training and performance analysis, where the model loss regression, ROC curves and comparison, the precision recall curve, and the model accuracy progression. So this is how the models are. We have the graph clip, the visual language GNN, graph transformer, and the VIGNN. They give us accuracies of 86, 87, 88, and 87.5%. So from our training, we found out that we have a best model, which was our scene graph model, performed the best, and it had the best F1 score, and also the AUC ROC was still the scene graph, precision was scene graph, and recall was graph clip, accuracy was still scene graph. This is the explainability summary dashboard, and these are the metrics. So the average model confidence was 71%, the prediction uncertainty correlation, top feature importance, which was 78 out of 100. Then the key insights were model flows high confidence with low uncertainty, strong clinical relevance, sharp analysis, and uncertainty quantification, which enables reliable clinical decisions. Statistical significance analysis gave us this graph, whereby the regions of interest gives us also the score, and also the p-value and the significance value per region. The clinical interpretation recommendations, the high clinic confidence, which is F1, is greater than 0.8 and is ready for clinical deployment. The moderate ones, which are less between 0.6 and 0.8, requires additional validation. Then the ones less than 0.6 need improvement. So we got the average score 0.79 as our goal. The comparative model comparison is that, and these are still the graphs that show the different comparisons, the F1 score for the micro, macro, and accuracy, and recall and precision. Results decisions, mobile optimization, performance analysis, where the mobile architecture speed up was 7.7 times faster, and also the inference results, whereby it was inference time was 15.20 milliseconds. So the primary model was the field graph transformer, and the conclusions is we have 45 distinct retinal pathologies with greater than 80% accuracy, and also 3.3 times expansion over existing approaches. So that has been our conclusion, and greater than 80% accuracy retention after optimization. The limitations will be regulatory approval, internet independence, geographic bias, and equipment variation. Then also the temporal scope. Those ones will be our limitations that we found. And for the next steps, we are going to develop preserving federated learning framework, enabling collaborative model training across multiple healthcare institutions without sharing sensitive patient data. Then we build epidemic monitoring systems for tracking disease prevalence trends, screening coverage, and intervention effectiveness at population scale. Yeah, so that has been it from me. Thank you very much. Thank you.